Okay, so why don't you take a couple of minutes and look over this first guy, and when I Alt Tab O, you guys can you guys see the solution, like this solution that I'm on right here, or can you only see the Word document? Only Word. Okay, that's good. Okay, so why don't you guys go over the Word documents for these for this first oh geez. For this first question. Also, if you have this midterm, I guess you can just look on your own copy. Do you guys need me to pull up this copy, or do you have your own? Okay, I'll just keep it open then. Okay, so how about these first few? You guys can feel free, like if you want to just unmute and talk, like that's totally fine. You can interrupt me. That's fine. So remember you remember the difference between big endian and little endian? Basically, big endian is essentially in order. That's how I remember it, and little endian is basically reverse order. So if we look up the top here, you can see that starting at int or ox 2010, that's where I starts at. So basically, I is going to correspond to these four. Char C is going to correspond to these four, and then int star j, because we have a 4-byte pointer, 8-byte pointer, is going to correspond to these last four here. So if we look at this guy, we have I equals feed food, j equals whatever, c equals whatever, and then j equals whatever. So we're actually only setting I once. So that means that we're going to have feed food, feed food over here, because I is set once and then it's actually never touched again. But on this end, we're going to do this backwards. Like that. Does that make sense? Okay, so what about these next guys? Let's see. We're talking about char C4, which is character array length 4 here. So the time we're setting this is right here. So how does that affect these next four? So it's shifted to the right by 8 bytes, right? So if I is feed food, if we shift this right 8 bytes, that's 1, 2, 3, 4. So we're just going to end up with feed, right? But what is on the left of feed? Because now we have to fill in the bits. So notice that this says it's signed. These are signed, right? So if you have feed food, you know that feed food is a negative number because of F. The F indicates that it's a negative number, right? That makes sense? So if we want to continue this being a negative number, then all the rest, if we shift it to the right, then everything that precedes those that we fill in, they also have to be Fs. You guys have gone over this in class, right? So basically, this is going to turn into FFFF feed. So this is going to be ED, FE, FFFF. Wait, 1, 2, 3, 4. 1, 2, 3, 4. Sorry, I think sorry, I made a mistake here. These are all going to be Fs, yes, but this guy is going to be F0. Right, because when we care about a char, that means that okay, so let me explain this a little bit better. Sorry, I made a mistake here. Basically, we're starting off with feed food, right? When we're shifting it over to the right, that is essentially making FF feed F0 because we're shifting over by 8 bits. But then this is this is a char array, so we're not actually taking all the data. So the data that we're taking is just this last guy, right? F0. So what we're going to end up with is FF, 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 F0. And it's in little endian notation, so we flip that around backwards, and what we get is FF, 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 F0. Sorry, I did bad math in my head. I was thinking that you shifted over too much, but we're only shifting over by 1 byte, 8 bits. Do you guys see how I came to that conclusion? No. Okay. Thanks for your honesty. Okay, so what specifically? Like you can unmute and chime in if you want, if it would be easier. Basically, we have to shift this over by 8 bits, which means that we are shifting it over by 1 byte, right? So this shifted over by 1 byte is this. Maybe it's easier if I split these up 1 byte at a time. Okay, so do you see how this, if we shift this over by 8 bits, 1 byte, that becomes this? Yeah, okay. And then because it's a char array, we're only saving the data of this char. So then all these just turn into Fs. And then what we get is F0. Also, don't feel bad if you didn't get this question. This was actually my midterm back in 2019, and literally none of us got this question right. I think we got most of this, but this one in the middle was very confusing. So don't feel bad. Okay. Why do we need to do a signed extension again? Isn't the F0 stored? That's a good question, because like the question is, why isn't this just unknown? And sometimes in C, it's just the way it is. C is very nuanced, and sometimes you just have to memorize these things. I'm not sure the exact logic behind this, but I know that this is the behavior that it exudes. So for this one, this is basically just going to be backwards. We're going to have FF, 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 and another weird C behavior. This one is going to be unknown. Starting at J, so we're going to have we're going to be setting two things here. J is going to equal the int pointer, like so we're going to be casting this to an int pointer, and it's the address of C0. Okay, so the address of C0 is 2014. Sorry, OX 2010, right? This is 2010. This is 2014. This is 2018. So we're saying that this is cast to an int pointer, the address of C0, which is 2014. This should be 00002014. Yes. And then we're going to say that the address that J points to. Okay. So I think this is why we're getting our unknown value over here, is because we're actually, when we say that we're changing the value of J, the value J actually is the address of C. So we're changing the value of what J points to, which is also C, because it points to the same thing. This is very confusing, I know. But let's just talk about J for a second. No, char is 1 byte. Char is always a single byte. We're storing F0 into a single char. Well, basically, this is the single char, right? This is like for little endian, it's this one, and for big endian, it's this guy. So we're just storing this char, but then we're keeping it signed, so we're extending F's over to these guys, because C is weird like that. But J is actually fairly straightforward. We're saying that J equals this, so this guy is just going to be 0, 0, 0, 0, oh, sorry, 2, 0, 1, 4. Do you guys see how I did this one? And because we're not changing J around at all, then we're going to have the same thing, 0, 0, 0, 0, 0, 0, or 2, 0, 1, 4. Does this one make sense? So I think these two are pretty straightforward. Whoa, 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 whoa. These two are pretty straightforward. These two. And then there's some weird behavior going on with this guy. So this guy, we're also doing star J, which is basically the value of C. So this is also like saying this, because star J is the same thing as C, because they're both addresses that point to the same location. We're saying star J or oh, Jesus. So we're casting the value of C to an int, and we're saying or the value of J. Oh my God. The unknown comes from that's a good question. To be honest, I don't think I can. I don't think I can perfectly explain this one. It's just sometimes this is C's behavior. Sorry, I don't think I don't think I can be a better help on this one.
Hi.
Hey,
Can I so from 2010 to 2013, that should be the integer I, right? And then
Yes.
from 14 to 17, I'm a little bit confused with like,
Yeah, this
what,
is I.
yeah.
And then this guy is 1, 2, 3, 4. This is C. And
Like,
this
how does
is,
it how does it become like having all the F's in the front instead of like just a simple shifting?
sorry, can you say it again?
How does that become like all F's in the front instead of just like a simple shifting and it has its like original value?
Yeah, okay. So this is honestly, C has just very weird nuances in syntax. So because we C is a char array, when we say that a char equals an integer, we're actually only taking 1 byte of the data. Does that make sense? So we have what we have is we're taking so we have feed food. We're shifting that right once. So then we have ff feed f0. But now we're only, because this is an int, right? Int 4 bytes. But we can only store 1 byte's worth of data because this is a char array. So what's going to happen is that we're going to continue these, filling them over, basically filling them so that they're still signed, and we're only going to take the last byte's worth of data. So basically, because we're little endian, we're taking this guy and we're only storing this guy, but we're going to keep the sign going for the rest of them. It's very weird and not very intuitive.
Okay. Okay, explain the unknown again. Like what's
Um, honestly, I can't quite remember where this unknown comes from, and everybody got this wrong on this one. I think this was like an extremely difficult example that maybe isn't the best. Why don't we, if we're still confused on this, we can go over a different example, because I know this one is I think this is mostly just bad example. The class average for this midterm was like 50%, and for this question it was like basically zero. At least like nobody got this section right. Um, okay. How about this type of thing? So global variables and an array. How do you guys feel on the minimum number of memory reads? Why don't we take a minute and do both of these? So translate this guy into assembly, and also try to see how many memory reads this is going to use. Yeah, so for 2b, this is actually the one that we're doing the minimum number of memory reads, not this one. Don't worry, I made that mistake last time. So we're saying the minimum number of memory reads for this guy. And notice that for this, we are corresponding to this data type up ahead. So B is a pointer, I is an integer, and A is a static integer array. Okay, so one thing that's always very important to keep in mind is exactly where you are in terms of memory loads and pointers. So this can get confusing because, so remember that I always like to keep a good amount of comments. So here I'm going to say R0 equals address of I. That's very important because it's not the value of I, it's the address of I, which is very different thing. So here we're going to say R1 equals the address of A. And here we're going to say that R2 equals the address of B. Okay, so what do we need for translating this? First off, we definitely need the value of I, but we're not actually setting the value of I, or so we're not actually setting any value to I, so we don't need to keep the address of I. We can just get the value and then we're good. Okay, so let's overwrite, is it brackets? Yeah, okay. Load R0 into R0. And now R0 equals value of I. Great. So likewise, we just need to load AI, and then we don't need to touch A anymore. So what we can do is we can do an offset load from A R0 or into R1, which means that we're doing R1 equals AI. Do you guys see how I got here? So basically, I load the value of I into here and then do an offset load to get AI into here. Okay, great. Now we're going to, so this is the part where people get tricked up on. So we're loading B. Now we have the address of B in here. Now we're going to do a load on R2 into R2. Now R2 equals B. So it's the value of B, but the value of B is an address. So now if we did a third load, now we would have equals whatever B points to. Does that make sense? So notice that we're doing two loads to get the value of I, but we actually, because B is a pointer, we have to do three loads. So if B was a double pointer, then we would have to do 4 loads. So basically, because we have a star here, that means we have to do one extra load to actually get to the value. But we don't need this value. What we need is this guy. So we're going to so what we need is B. So BAI. Then we're going to subtract 1 from that. So we're going to load R2 offset R1, and we're going to load that into let's call it R3. So now R3 equals BAI. Is that good? Makes sense? Now we're going to decrement R3. -1. And lastly, we're going to do a store of R3 into We still have B as R2, so we're going to store that into R2 offset I, which is R0 and 4. Okay, so now we're saying B I equals B I minus 1. Okay, I would encourage you guys to make sure that you actually write comments out for these, because it's very difficult and it's easy to get tripped up when you don't write the comments out. So like if I didn't write the comment out, I might have forgotten that B is a pointer. I might have only done one load when I'm supposed to do 2 loads. So I think the hard part and the tricky part right here is this right here. So do you guys understand why I did 2 loads right here instead of just 1 load? Because it's a pointer. Okay, great.
Hi, Brent.
More time on this?
Question.
Yeah, what's up?
So I always get this confused. I guess when it's with assembly, let's say you're doing like pointer arithmetic, so B, then bracket like, I don't know, or like B plus 1. Aren't you getting the next address away from B? Are you getting the value in that address?
If it's an address, then incrementing by 1 won't get you the next address. Incrementing by 4 will get you the next address. However, if you, let's say you have R0 is, I don't know, some address. And let's say R1 equals 2. If you do, let's call this OX 1000. So if you do an offset load, so if you load R0, R1, 4 into R3, now R3 equals the value stored at address OX 1008. Does that make sense?
So B, if you're doing like B plus 1, wouldn't that get you the next, like wouldn't that increment it for you, because it takes into account pointer
plus 1, no. When you're adding to it, you would have to explicitly, like if okay, so if R0 is OX 1000, Inca R0 makes it 1004, right? But just incrementing R0 yields 1001. So that's actually not the next address. So when you're adding numbers to it, so if you want to make R0 1008, you would need to go R1 equals load 8 into R1, and then you do what's the command? Is it add? So I can't remember the exact syntax. You'd have to do an add command, adding R1 into R0, which would yield R0 equals 1008. So yeah, the difference is when you're doing adds, you have to be explicit with how many bytes you're using. But when you're doing offset loads, remember that this 4 is essentially telling you it's how many bytes that we're going to be moving each one by. So if R1 is 2, that means that we're doing 2 times 4 equals 8, and then we're adding 8 to R0, which is 1000, and then we're going to be, and so that's the load that we're doing. So now this is essentially 1008. Does that make sense? And yes, if B wasn't the pointer, then you would not need to do load R2, R2, and everything else would stay the same. Yes. So what you use what's the right word? You use indexes when you're doing an offset load or an offset store, like this or like this. Notice that R1, we're not multiplying R1 by 4, but another way to do this would be basically if we multiply R1 by 4 and then do add R2 and then add R1 to R2, then do a load, or sorry, then do a load of just R2, then that would be the same thing. But it's much easier just to, instead of doing this whole thing and multiplying it before, it's just easier to do an index load like that. Oops. Do you guys need any more clarification on this whole thing? Because I know this gets very confusing. How about 2B? How many do you guys think it is? So let's break this down and look at exactly how many loads we're doing. Oh Jesus. It is not 6 actually. It's close to 6. So let's see. Okay, so we're starting off by looking at A, right? So to do the access A0, that's going to be a single load. So A0, why is this so tiny? A0 is going to be a single load. Then B is a pointer. So remember, if we wanted to get the value that B points to, we have to actually do 2 loads because B is a pointer. To just point to the array that B points to, we have to do a single load. So just to get B, that's a single load. Now we're pointing at B and we want to get BI, which is just an index off of B. So that's another load. So BI is another load. Another load is actually BA0. So A0, that's another load. And because I is an integer and we're getting the value of I is our 5th load. Did you guys get all these? Even if you got 5 as the answer, was it specifically because these 5 reasons? Because sometimes for this you can get the right answer for the wrong reasons. So do all these 5 make sense? Do you guys want me to spend any more time on this? Feel free to speak out. You don't need to load B twice because you're not getting the value of, well, actually you are loading B twice. So you load B once here, and then to get the value of B, you would load it again here, and then you load it again here. So you have B, and B is pointing to an array, right? So now in that array, you have 0, 1, 2, 3, 4. So first off, let's say I is 0. So we're going to be accessing that. So that's 1 load. And then we're accessing A0, which let's say is 3. So we're accessing this value. Yeah, no, load B isn't reading from memory. You're right. So this does not do a memory read, but this one, it does do a memory read. Because this one is just loading the value that B points to. But actually doing this load command is what makes it read from memory. So yeah, this is a single load because it's a pointer. But notice that we don't have to load A because it's not a pointer. It's just a static array. So we're already pointing to the array. Then we just have to do an offset and load whatever value that we want from A. But to get to that array for B, we have to do a load first just to get to the array. We have to do a memory read just to get to the array. Then we do more memory reads to get our offset. It's a pointer to go where it points, then yeah, exactly. Yeah, no, you're good. As long as you guys get it. Okay, so let's look at these structs. I think we can just go through these all together. So what do you guys think the struct size of struct A is? So notice that ints and pointers are both 4 bytes long. So this is going to be 2 bytes. Okay, so this is going to be 2 bytes. This is going to be 8 bytes. So what is the size of struct B star B? What's the size of this guy right here? 4, right, because it's a pointer. But in struct B, what's the size of this guy, struct A? It's the actual size of the struct, right? Because because struct B is literally putting an entire struct A into struct B. But here, it's a pointer to a struct B, so it's only 4 bytes. And then char E is 1 byte. However, remember, so if we look over this, the largest member of this struct is 4 bytes. So an int is 4 bytes, a pointer is 4 bytes, char is 1 byte, char is 1 byte. So we have to make sure that every single thing, every member here has to start on its memory address divided, sorry, a memory address that is divisible by itself. So let's say this starts at OX 1000. So then we have OX 1001, which is C1, and this is C0. But here we can't put in int. We can't put in this int array, right? Because it is aligned to 4. So basically, we have to put 2 bytes of padding here. What? Why is it doing that? So we have to. I don't know. Well, let's just type padding. Now we do D1. Actually, it's D1. Okay, this is going to get a bit dramatic, but you guys see why we have to put these 2 bytes of padding, right? Because we have 2 chars, and then we need 2 bytes of padding in order for D to start at a byte, an address that is divisible by its size, which is 4. So then after that, we do struct B, which is just 4 bytes, and then we do char E. So if we finish off with char E, then we need to add 3 bytes afterwards to make the entire struct be divisible by its largest element, which is an int or a pointer, which is 4. So this is going to be 4 bytes, this char C2. This is going to be 8 bytes. This is going to be 4 bytes, and this is going to be 4 bytes. So we have 1, 2, 3, 4, 5. So that's 20 bytes. Does that make sense? So now struct B, we have 20 bytes, and then we have 1 byte, and then 4. So when we have a struct in here, we don't need to align everything to 20 bytes. How we deal with this is we need to align struct B to either the largest element in struct B or the largest element in struct A. Luckily, they're both 4. So the largest element in struct A is either this pointer or this int, which is 4. And the largest element in struct B is this int, which is 4. So we're going to align this struct B to 4. So this is size 20. This is 1 byte, but the next one is an int. So we need to align it to 4 bytes. So we need 3 bytes of padding. So 20, 4, 4, 28. So this is size 28. Let me double check. I'm fairly certain I'm right. Yes, I'm right. Okay. Does that make sense? Okay, so what about offsets? So if the beginning of struct A is 0, so char C is 0, what's the offset of D1? Well, D0 is going to be 4 and D1 is going to be 8, right? So that's easy. That's 8 bytes. Hypothetically, with struct A, we had long E instead of char. Yes. Well, yes and no. So that would actually only increase the size of struct A by 4 bytes. If a long is 8 bytes. So remember that we only have to align each member to its address that is divisible by the size of itself. So that means that I'm going to pull up a. You guys can't see this, can you? Okay, can you guys see my whiteboard? Okay, so if we have, let's say char C, and then we have int I, long L, and then another char C2, let's say. Sorry, this is very messy. So char C2 is going to go right here. Sorry, char C1. Okay, whatever. So that's going to fill here. And then we're going to have, how many bytes of padding are we going to have after this? So notice that this is 1 byte. This is 4 bytes. This is 8 bytes. And this is 1 byte. So how many bytes of padding are we going to have after this? No, actually. Because remember that we have to, if this is 1,000, we have to align, 1,000. We have to align each member to an address that is divisible by itself. So we put padding, 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 and this is 1,004. So is 1,004 divisible by 4? Yes, it is. So we can actually put int I here. Now we have long L. So that's at 1,008. Is 1,008 divisible by 8? Yes. So we divide, so now we can put long L, 1, 2, 3, 4, 5. I didn't draw enough spaces. Let's continue this a little bit down here. So now this is 1, 0, 1, 0. And we have char C2. Now we have to put 1 byte here. Now how many bytes of padding do we have after C2? You think so, but no. So when we finish a struct, we have to make sure that the entire struct is aligned to its largest member. So its largest member is a long, which is 8 bytes. So we actually have to put 7 bytes of padding after this. So 1, 2, 3, 4, 5, 6, B, 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 B. Okay, so yeah, so 1, 2, 3, 4, 5, 6, 7. No, whoops, too many. Okay, so this size is this is size 24. Okay, so now here's the fun part. If we get rid of this, what do you think the size of the struct is? Exact same, correct. Because now we're just so now we're just getting rid of this, but the next member is a long, which is 8 bytes. So it has to be aligned to 1,008. So we have to put 7 bytes of padding. How about if we move this guy? What if we move this behind this long? Then what size is this struct? 16, correct. Because now this can slot directly in here. Then we have 6 bytes padding, then we have 8 bytes. Does this sort of make sense? So just remember that anytime you have an element, it has to be aligned to an address that is divisible by itself, like the size of itself, rather. So if it's 8 bytes, it has to be there has to be 8 bytes between everything. Generally, you're going to have 4 bytes though. So, oh yeah, I was checking the score. Don't mind me. Where is shift? Okay, so what's the offset of struct element E of struct A? Remember that this is 20 bytes. So this is pretty obvious. It's if this is aligned to 4 bytes and it's the last element, then our offset is it's not 20. Because remember, if you 20 offset, it will give you the next struct. So the last element is 16, correct? Yeah, 20 minus 4, exactly. So struct B, A dot C1. Here's a fun one. So what do you think this the offset of this guy is? remember that char is size 1, not 4. An int would be size 4. Yeah, offset is just 1. Because if we're pointing to a struct B, because a struct A is the first element, we're also pointing to the beginning of a struct A. So we're actually, because A is the first element of struct B, it's like we're pointing to the exact same element in struct B and struct A at the same time. Does that sort of make sense? Because struct A isn't a pointer, it is like literally inside of struct B. Like it's what is constructing struct B. So if we're pointed to A, it's the exact same memory address as A.C0. Does that make sense? So if we need A.C1, then we look at the size of C. It's a char, that's 1 byte, offset is 1. Would offset struct B dot A dot C? Yes, it would be 0. It's weird, right? So if we point to struct B, we're at memory address 1000. If we're at B dot A, memory address 1000. If we're at B dot C0, still memory address 1000. It's the exact same thing. In fact, if we load on B and then we do a load on B to get its value, then we would be getting the value of B dot A C dot C0. So what about struct B X? Remember that yes, so size, if we offset the size of A, we get Y, and then we need another 4 bytes to get X. So yeah, 24. Beautiful. Here we go. We're almost into some static control flow. Okay, why don't you guys try to do this real quick? I'll try to make this a bit bigger so it's easier to see. So we're using these previous, so we're using these previous structs, and we're doing this guy. So this might look simple, like it might look like what we did before, but it's actually very tricky, and a lot of people get tricked up on this. So take your time. Make sure you're doing the offsets correctly. And remember the difference between a dot and an arrow. That's also very important. Okay, so let's tackle A first. So first off, we know that A is a pointer, right? So what does that mean? So that means that we have to, let's type out these comments. Let's type out these what, why is this? What? Sorry, Word is being really, I don't know why, okay. So that means that R0 equals the address of A. Then we have to do another load. Now R0 equals A. So now we're doing A to B1.x. So here is the part where we could do this a couple of different ways. So one way we could do this is actually we have the address that A points to. Now we could just add the offset in and then do a load. But remember what I was talking about before with offset loads. So instead of doing that, what we could do is just we could put the offset in and then do the, why is this doing that? Okay, and then we can put the offset in there. So now the question is, what do you guys think the offset is for us to get A to B to get A to B? So what's the offset here? So we just want, so afterwards we're going to be pointing to the B struct. Yeah, it's going to be 12. Remember, because if we're starting here, we're doing 4 bytes to get to int here, and this is 8 bytes. So then it's another 8 bytes to get here. So now remember that a pointer is a dynamic array. So this struct B star B, it's actually pointing to a dynamic array of structs. So because we have B1 here, that means that this is an array of structs, and we're looking at the second struct in this struct B array. Does that make sense? So now we're going to do, another load. So what is our offset going to be? What we're going to end up with is A to B dot X, B1 dot X. So now this is where people lose their marks. So what's the offset here? It is not 28. So remember that we have to skip an entire struct B, and then we're going to X. So we're skipping an entire struct B, which is 28 bytes. And so if we wanted to load B1 here, there's a couple of different ways you could do this. If you wanted to load B1 here, then you could do this. Wait, no, you couldn't. No, that is completely wrong. Sorry, don't listen to me. So yeah, exactly. So what we're going to be doing is, yeah, exactly, Sean. So we're skipping the entire first struct B, which is size 28 bytes, and then we're skipping struct A, 20 bytes. Then we're skipping char Y, which is 4 bytes. Now we're getting B1.x. So we're skipping 52 bytes. Does that make sense? This is a weird one, I know. So the key part is you have to remember that B is actually a dynamic array. And then because X is not a pointer, so to get the value of X, we skip ahead all the way to X and then load that value into it. If that doesn't make sense, speak out. Otherwise, we're going to move on. So now we have that value. Now we're going to shift left. Is it R0 and 2? No. That's 2R0. Yes. You re-explain B1. Okay. So basically, let me switch over to oh god, you guys are gonna see all my Dungeons and Dragons tabs I have open. All right, basically, if we have a struct B, just size 28 bytes, and then B is a struct A, then it's a char C, then it's int X. So let's actually take a look at this in memory. So this is 20, this is 4, this is 4. So let's look at what this looks like in memory. So this is B, and B is a pointer. Actually, B is a pointer, and it points to the beginning of this array. Now B is a dynamic array, so it's an array of struct B's. So this is B0, this is B1, this is B2, etc. With me so far? So we do load BR0 to get here. If we do another load, now we're here. Exactly, we skip an entire B. So now what we want to do, our command is load 52 R0 into R0. So basically we're skipping all of this, which is 28 bytes. And then here, so this is our A, and that's 20 bytes. And now we're at C, and then we have another 4 bytes. And now we're at X, and that's the last 4 bytes of this. Does that make sense? So basically we're skipping in one command, we're skipping all the way to X and doing a load from there. Okay, so now we're not quite done. We have to finish off. There's just a couple commands. Basically, so now we have B. So B is not, so B is not a pointer. So we're going to be storing in B. We're going to be storing the value of A to B1 dot X shift left to 2. We're going to be storing that entire value into B dot X. So what is our offset? I want to retype that. All right. So what's our offset? Do we just assume that B is a pointer to a contiguous array of structs? Well, that's the thing. That's the thing with C. C is weird. So it could be pointing to 1, but it could be pointing to an array. You don't know that. There's generally more context given. Like you'll see if there's a malloc to see if you're allocating a single element or if you're allocating an array. But not always. Like sometimes the reason for a dynamic struct is that you have, or sorry, a dynamic array is that you have it and then you can keep adding to it. So yeah, like it, but it's sort of the same thing. I mean, like if you're accessing the first, if you have a large array and you're accessing just the first value of it, that's like the same thing as if it was just length 1, right? Because it's just like like if it's like b dot x or it's b dot x 0, that's sort of the same thing, if you see what I mean. So it's weird that it can sort of be both a dynamic array and pointing to and just one, but essentially, yeah, you should always assume that it can possibly be pointing to a contiguous array. Yeah. So what's our offset in this last one? So we're storing into b dot x. So that means that we are offsetting 24, exactly. So 24, then we're in x. So now we're going to offset at 24. Does that make sense? We all Gucci. Last comment. 1 equals ampersand b. Okay, beautiful. So now we're going to go into some static control flow. I think I deleted. Ooh, this looks kind of ugly. Here, one sec. Let me okay, there. I think that's a bit better. So let's take some time and go over this guy. Yeah, for sure. Just remind me at the end. And yeah, I'll stick it on the UBC BCS page. I got to double check though, because this thing does have a gigantic do not share with anyone on the front of it. Oh no, it doesn't. That's the other one. Okay, now we're good. How you guys looking? Okay, so the first thing we're doing is establishing, because we're starting straight at the for loop, we have X already. And we're going to be storing X into Y and then starting off the for loop, and Y is going to be a variable that's changing throughout the for loop. So first off, we're going to do a store, and we're going to store R0 into R1, which makes Y equals X. So now we're actually going to start our loop. So the way we start a loop, so sorry, just give me a second to take a look at this for a sec. Right. Okay. So we have the value. Well, let's just do another one. So we're going to load. Yeah, because we've stored X into Y. So X and Y, essentially, they're the same thing right now. So I guess technically we could be working with both, but let's work with Y because it's going to be easier to read. So the reason I'm redoing this load is because I want to start this. I want to start this loop over. So just in case I mess up, I mess around with Y's R0 or R1 in the future, I'm just gonna explicitly restate that R0 is address of Y. Then we're going to do a load. So now formatting of this is driving me crazy. I'm not sure why it's like this.
Hi, sorry, I'm still confused with that. When it says Y equal to X.
Yeah.
Shouldn't it be like it's like the address that X pointing to equal to like Y? I don't know.
Yeah, that's a good point. I think there's multiple ways of doing this, and as long as you end up with the actually, yeah, you're right, because the way they do that is they do a store command. Because you're saying that it should be like that, right?
I think when you make
Yeah.
pointer equal to another pointer, that it technically does that. Like Y is going to be pointing to the address that X is pointing to.
I'm not gonna lie, I'm reading straight from the solutions. So generally I go straight to the solutions, but no, that's a very good point. Let's try to break this down, see why they did that. So here we have, so we're actually, yeah, we actually have X, and then we're loading Y, and then we're storing X into Y.
Oh, they should be pointing to the same thing. So whatever the X value is, it should be Y as well for now, I think.
Yeah, I think there's multiple ways of
Uh,
doing this. Like, I think this is a bit extra, and you don't necessarily need to do this because, yeah, like you just need the address, right? Like, so we could just say that because Y is a local variable. Oh no, Y actually is a struct that we've established here. Okay, so we do need to set Y equal to X, but it's just the it's just the address. That's kind of strange. Yeah, my understanding would be that you would basically skip. Oh no, sorry, because it's a pointer, right? So we're not actually storing the value of X. So this is correct. So what we're doing here is we have the address of X. Now we've loaded the value of X, which is an address. So now we're storing that address into Y. So now Y equals X. So if, okay, let me break out. So this is when pointers get confusing. Let me break out the this guy again. Oh my God, where's the? Clear. Okay, so actually, so let's say we have Y. Then we have Y is a struct, right? So this is, I don't know, some struct. And then we have X, which points to another struct. So we're doing the command Y equals X, right? So first off, we're starting here. We're starting in this arrow, which is pointing to the address that points to the struct. And likewise, when we do, so this command is load, let's call this Y. This is X. So this, we're doing load Y into R0. So now we're loading, so now we have the pointer that points to Y, which is a pointer that points to a struct. So when we want to get the value of X, we have to do another load because this is like, oh, actually like OX 1000 or something, right? So what we want to do if Y equals X, we want to take this value and we want to put it over here, right? That's the goal. So what we need to do is we need to do a load X into R1. So now we have, let's say this is OX, I don't know, FEAD 0, 1, 2, 3. So this is just something in the heap, right? So now we have this. So if we do another load command, load R1 into R1, now R1 equals OX 1000, right? You guys follow me so far? So we do two load commands because X is a pointer. Now we have the address of this struct in R1. So now what we want to do is take this and put it into Y. So we do one load and now we're pointing to Y. And now we're saying, okay, we want to take the value and put it through this pointer into whatever that pointer points to. And the pointing we're pointing to is Y. And Y is a pointer. I know I'm saying pointer a lot. I'm sorry if this is confusing. And to do that, then we just do a store in R1 into R0. Does that make it any more clear? It's very easy to do get pointer stuff wrong. Like it's so confusing. Because like if you think about the way I think about these is like if you just have int x, right? So this is like, I don't know, 4 or something. And then you have int star p, which is a pointer that's pointing to another pointer, right? So like the address is stored here and the value is stored here. But for this one, the value is just stored here. But in assembly, in order to get that value, you need to do 2 loads. So like you need to, so you're starting off here and then you got to do another read to get here. But for a pointer, you need to do a read and then a read and then a read to get that value. So yeah, it can be confusing. So you got to make sure that you kind of like move traveling across these arrows in the right number. Okay. Okay. So where were we? So we have y equals x. Great. So now we need to, so we're loading y into R0. We're going to load. This is a case where we need to do the store here since it's a global variable. Yeah, so we need to store, well, I mean, we need to follow what the code is doing. Like we're doing x equals y, so we need to put x into y. We need to overwrite the value of y with x. So we're just following along with what the code is doing. Section of 1D, what we're testable. Oh yeah, can't answer that for you. Okay, why is this being so annoying? Let's just pretend I put a comment here. I don't know why Word is not agreeing with me right now. R0 equals y. So now we are going to do a check. And eventually we're going to get around to, let's put it down here somewhere. So when we're done. So if, remember in C that's saying y does not equal to 0, null can be like the same thing as y is not equal to 0. So basically this is saying if y equals 0, then we're going to jump to done. But if it doesn't equal 0, then we're going to continue looping. So this is basically if y equals null / 0. Essentially, like if it doesn't exist, go to done. Does that make sense? But if not, then we're going to continue with the loop. So we're going to do an offset load from y to get a. So where is a? It's the so y is of type struct x. So a is its first element. So we're going to do an offset load of 0 in order to get a. 0 R0, and we're going to store that into, let's say, R1. So what that's going to do, that's going to say R1 equals the value of y.a. Sorry, y pointing at a. Does that make sense so far? Now what we need is we need a plus 3. Okay, so this is pretty straightforward. We're going to do load 3. You don't need to do, you can't just do this. I'm just being explicit because I'm saying we're doing an offset load of 0 because we're accessing the first value. So I'm just trying to be a bit more clear with exactly what we're doing. So I'm going to say load 3 into, I don't know, that's R2, sure. R2 equals 3. That should be loaded. Now we're going to add R3 sorry, R2 into R1. And that's going to yield R1 equals y to a plus 3. Did I do that in the right direction? Or add R2, R1? No, it should be R1, R2. So we're adding R2 to R1. Oh no, I did have that right. Sorry. I've got Y86 from comp sci 313 on the brain. Stuff is kind of backwards. Okay, so now we're going to say that if y to a plus 3 is less than or equal to 0, we're going to call foo. So we're going to do a break be greater than R1 next. So I guess we got to move this down a bit more. Let's put next somewhere. Back. Okay, so what this is going to do is basically call foo. Oh no, sorry. If sorry, go to next. Does this make sense? Actually, I think if I include the next line, it's going to make more sense. So now, basically, this is saying we're sorry, yeah, I haven't really completed this. So this is basically saying that we're skipping this. We're skipping foo, right? So now we're going to have GPC 6 R6 and then JFoo. Yeah, remember, so we're saying GPC 6 R6 because 6 is the size of this guy right here. So basically we're saying we're going to call here, and then when we return, we're going to skip 6, which is the size of this command, and then we're going to return to this next one, which just so happens to be next. So now we're going to continue. So basically what we have to do here is we have to continue the loop. So we're going to do y equals y to b. So remember when you, so the reason I explicitly redid this here was because what if foo messes around with R0? So you always, like after you do a call, you want to make sure that you explicitly state, restate your registers, just, well, except for R6, just in case the function call that you do messes around with your registers. So I'm going to do a load y into R0. Then we're going to do a load R0 into R1 because we're going to need y later. We're going to do a load. What exactly we're doing? So we're saying that y equals y arrow b. So b is 4 bytes off of it. So now we're doing an offset load size 4 of R1. We're going to store that into 1. And now we are storing R1 into R0. Okay, let me type some comments up for that. R0 equals y. R1 equals value of y. R1 equals y to b. And this is y equals y to b. And now we are going to break back to loop. And done is just going to be a halt command. How do you guys feel about this one? Does this make sense? GPC. So GPC is, to be honest, I can't remember exactly what it stands for, but we're storing the current. Okay, so actually no, PC stands for. Someone wants to help me out. That would be great. Let me check. GPC. Well, it generally won't be more than 6 because the only time you're going to be using GPC is going to be directly before a jump command. So basically what we're saying is we're storing the current we're storing the current address that we're on. So like if this is like OX 1000, this is OX 1004 or 6 or whatever it is, blah 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 blah. Say this is like OX 1024. So what we're going to be doing is we're storing the current address that we're on plus 6 into R6. So now R6 equals OX10 2A. Does that make sense? Okay. And the reason we're doing this is because when we call foo, we need a place to go back to. So 102A, that's the address of this line right here. This line right here. So when we do this function call, we got to make sure that we're not overwriting R6 because that's our return function. So at the end of foo, we're going to call basically we're going to return to R6, which is 102A, which is going to be this value. So we're going to do whatever we want in foo, and then we're jumping back and then going into this guy. Does that make sense? Do you guys want me spending more time on this, or does this make sense now? 6 is the size of a jump command. This command right here, it's 6 bytes. And it just is. If you have, I don't have the sheet available, but if you guys have like the cheat sheet, it should have like all the, oh no, you guys have like a big book, right? So there's a table somewhere in that handbook where it says all the commands and the size of their the size of the commands. So if you go to that table, you'll see the jump is a 6 byte command, and that's why we're doing GPC 6. Everybody good with this? Want me to move on? I'll take that as a yes. Let's do some pointers. Hooray! Oop. Just ignore this. Pretend you're not watching. Okay, well. So basically for this one, we're going to look at the pointers and we're going to see what has changed. So take a quick look at this code, and basically you're recording which the final value of B and what, if any, of these numbers have changed. All right, so take a couple minutes, go over this. Okay, so what is the final value of B? Oh, sorry, the final address. No, sorry. Value of B, which is an address because it's a pointer. So first off, we're saying that B equals the address of C4. So C is at OX 3000. And then 4 is going to be offset, 1, 2, 3, okay, well, 4, which is, so it's going to be 3010. The second line, B minus 2, that's actually not changing the value of B. That's changing the value that B points to. So now B equals B minus A1. A1 is 3. So we're going to be subtracting 12. 12 from that. So B starts off as OX 3010, then OX 3010 minus 12 equals OX 3004. And the third time that it changes, this doesn't actually change the value, but this does. So we're doing B equals B plus 1. But because B is a pointer, it's of size 4. Now, I think this is what you're talking about before. So now this OX 3004 plus 1, as in one value of the thing size of whatever it points to, equals OX 3008. Which is weird, but that's how C functions. I know this one can be a bit confusing. Does this make sense?
Yeah. Sorry, can you explain the 3010 again?
Okay, so we're saying that B equals the address of C4, right? So C0 is OX 3000. So C1 is 3004, C2 3008, C3 300 maybe C, and C4 is 3010.
Oh, it's hex number. Sorry.
Yeah, exactly. Yeah, always think about these in hex, because it's easy to say, and actually don't even say 3000, because 3000 kind of implies decimal. I know this is a trap that I fell into, so I would say to myself like, oh, it's it's 3010, and then I would minus 2, and my answer would be like 3008, but actually it would be 3000 and D, right? So I would encourage you guys to always think in hex, because especially on these midterms, these finals, it's very easy to think of it as a decimal number and then just do some wrong math and then end up getting the wrong answer. So does this make sense? We're doing 3010 minus 12 and then plus 1 equals 3008. So the weird part is that 3004 plus 1 equals 3008. That's because it's an address. So, sorry, it's a pointer. So when we increment a pointer, it's actually increasing it by 4 bytes, which is the size of whatever it's pointing to. Because C. Okay, so we know that B equals OX 3008. So what has changed? So the nice thing is we can look through this and it's fairly clear to see that A doesn't change at all. At least over here. But if we say that B equals the address of A and then we change it, so that could happen. But that doesn't happen. Yeah, that doesn't happen. So so we can see that we're only going to be changing values of C. So we're saying that, I don't think I can draw on this, can I? Actually, let me do this. All right, this seems like this would be easier. Okay, so first off, we're starting with B. So B points to 0, 1, 2, 3, 4. So B starts off with pointing right here, right? 0, 1, 2, 3, 4. So this is OX 3000, 3004, 3008, 3008, 9, ABC, C, and 3010. So now we're saying B of -2 equals A0. Okay, so B, this is B right here, saying -2, so this guy equals A0. Okay, so C3 now equals 1. Sorry, C2 equals 1. So now we're saying B equals B minus A1. So that's just changing the address of B. We're not actually changing any values in here. So now we're saying C of B1 equals 7. So this means that C, and what is B1? Well, B points to right here. Oh no, but we've -12. Okay, so B did point here, but now we've -3 spots. So B actually points to 1, 2, 3. So B actually points here now. So B1 is actually C2. So C of C2, which is now 1, equals 7. Does that make sense?
Oh,
Yeah, no
sorry.
problem.
Can you explain how B1 is 1 again?
How B1, okay, so this is when you basically, this is why I wanted to switch over to paint, because like we have to draw this out, because otherwise it's very confusing, and it's still confusing. So basically, when we start out, B equals C4. So this is what B points to in this line, right? Now this line, we're saying B of -2. So -2 addresses from B equals A0. So if we -2 over here, that's pointing here now, right? This is B -2, right? And that equals A0. A0 is 1. So now we're overwriting 2. Now that value is 1. Does that make sense? Just gonna clean this up a bit.
Yes.
Okay, so now this value in here is 1. So now we're saying B equals B minus A1. A1 is 3. So because it's a pointer, we have to shift this over 3 spots. So 1, 2, 3. Now this is B.
Oh, got it. Yeah, then it's B1 is 1. Then yeah.
Yeah, it's weird, right? So now B1 is 1, so C1 equals 7. So yeah, C1 equals 7. So now we're doing A C1 equals B2. So C1 is, yeah, it hasn't changed. So A7, oh, I'm wrong. We are changing A one time. So A7 equals B2. So B is here. So B0 is 7, B1 is 1, B2 is 8. So A7 equals 8. That's what's happening right here. Okay, so now we're kind of doing the same thing. B is here. So we're saying B plus 4. So B offset 4. 1, 2, 3, 4. So this guy is now 6. So what's that in terms of C? 0, 1, 2, 3, 4, 5. Okay, so now we're saying C5 equals 6. And that's this guy right here. So now B equals B plus 1. So now B is going to shift over. Now B. So this means that B equals the address of C2. And now we're saying B equals star B plus 1. So the value of B is 1. So we're saying 1 plus 1 equals 2. So star B, which is the same thing as C2, equals 2. Okay. Where's my so C1 equals 7, C2 equals 2, C5 equals, what was it, 6, and then A7 equals 8. Does that all make sense to you guys? Beautiful. So it's been 2 hours, so I can keep going if you guys want. If there's anything specific you guys want me to cover, go ahead and make some requests. I think this next part is actually pretty important. We should probably go over this. What do you think? That's one person. Does everyone else agree? Do you want to keep going? I'll tell you one thing. I'm not going to go through the very last question because it is extremely it's like translate this whole thing to C, and it's a bit of a nightmare. It's very time consuming. And to be honest, I am not very good at translating assembly to C. It gets confusing. Okay, so let's. Okay, good. I don't have any answers written down here. So let's take a look at this. And let's do two, actually, let's do one at a time. We're going to take 30 seconds and we're going to see what kind of errors there are in here. So there could be memory allocation errors, there could be dangling pointers, there could be like maybe just some syntax is wrong. So your job is to find out what the error is and how to fix it. Oh, sorry, 30 seconds. I forgot about that time part. Okay, so what is the problem for this guy? There is no free memory leak. Let's double check. Exactly. So the R allocated in extract is never freed. No. This is C. This never does anything for you. You always have to explicitly do absolutely everything. Oh, okay. So we're not fixing the bugs. We're just pointing them out. Okay. So the stuff in bold is the stuff that's being changed. So what about this guy? What do you think the issue is? Also note that there might be no errors at all. So what do you guys think the problem is? So the issue is that, remember that 2 pointers can point to the same thing. So with that hint, can you guys tell me what the issue is? Okay, so the issue is, notice that we're saying that int star t equals r, and then we're freeing t. So t and r are the same pointers. They're pointing to the same thing, and we're freeing t. So if we free t, that's the same thing as freeing r, because they point to the same thing. So when we return star r, we're trying to reference memory that's already been freed. So basically, this code is referencing free memory because, because process frees it and then we're trying to return it. Yeah, so that's bad. Can't do that. What about this? What was this third one? Yeah, exactly. Dangling pointer. Sorry, not that was dangling pointer for B. What's the problem with C? So where exactly do you think a dangling pointer is? Okay, so what is the type exact? There it is. Yeah, so notice that it's actually an int. So it's storing the value of r as a local variable before it's storing r. So what's the problem here? The problem is nothing. There is nothing wrong with this code. This is perfect. So notice that we're saying we're storing the value of r that we get in extract. We're storing that value into r2, which is a little local int. Then we free r, and then we return the value that r used to point to, which is r2. So that's perfect. That's exactly what we want to do. Okay, what about 6D? So the issue with D, notice that we're changing malloc to a local variable. So there's a couple of problems here. So first off, we're returning a local variable as a pointer. So instantly that's going to be a dangling pointer, because the memory that is allocated to this pointer, when the function completes, it's gone. It doesn't exist anymore. The second problem is that we're trying to free it. So actually, if you didn't have the free line here, this would still be your problem. So there's two problems. One problem is that there's a dangling pointer because because it's a local variable that we're returning. The second problem is we're freeing it, and we can't free a piece of memory that's not allocated by malloc. Okay, what about 6E? It was dangling because if you look at 6D extract, it's saying int star r equals, oh, you know what? That's my mistake. I didn't notice that A was being passed in. So there actually, yeah, that's my mistake. There actually is no dangling pointer. If we were just saying that that star r is a local variable and then passing it back, then that would be a dangling pointer. But because we're passing A into extract, and that we're just saying that r is an offset of A, then that's actually okay. So that's my bad. It's not a dangling pointer, but it is still a problem because we're trying to free something that wasn't allocated. see how they've defined it. Memory leak, dangling pointer, or yeah, other memory. Actually, would it be a memory leak? No, it wouldn't be a memory leak. So yeah, it would be another memory error, which is you can't free something that hasn't been mallocked. Okay, so what about E? So this one is a little exactly. So we have to remember that you don't know what happens in Magic. Exactly. So it might free it, and then we might be doing a double free. Or what if Magic what if Magic saves it as a local variable into a class? Then other methods might be trying to use R, but we've just freed R. So then it's going to be then in that case it's a potential then it's a potential dangling pointer because it's being freed. So actually what you I'm not sure if you're talking about two separate instances, but it is two separate instances. So one instance is that it's a possible dangling pointer because Magic might save it as a local or a class variable. And the second one is that if Magic frees it, then we're going to try to free it again, and that's bad. So two cases where it could be bad there. And last one, 6F. Nope, that's the value. That's the first value in the R array. It's not the same as R. Exactly, it's good. Because we're just passing the value in, doesn't matter. So I think all of the midterms in the past few years, they've sort of been the same format from what I've seen. I haven't checked the one from last semester, but all the ones from the previous like 3 years were sort of this same one. So I've got some other stuff to do, but if you guys have some last questions, you can go ahead and ask. Otherwise, I'm going to sign off and do some C++ work. But I do not mind staying for some extra questions if you have any. Awesome. Yeah, no problem, guys. I will good luck with your midterm.